we're given a bunch of integers, a1, a2, all the way up to an. And how do we actually find out their greatest common divisor? Can we find out using their linear combination, meaning we can multiply each candidate by some integer and then add them all up? Let's just call that a linear combination. Well, the answer is that yes, we can actually do that. And after we found these integers, even though we don't know exactly their numerical value, but they exist, so that their linear combination equal exactly the GCD. Also, that GCD is equal to exactly S0 is defined as the minimum possible positive integer from their linear combination. So if we choose some random integers and multiply each candidate and add them all up, we can end up with either positive integers or negative integers, or possibly zero. So out of all the possible positive integers, there exists a minimum element. So that's what I mean by S0. So the question is that, are there actually positive integers coming out from the linear combinations? In other words, is this set empty? Right? Because I need to know that there exists at least one element in this set. The answer is yes. If we just call x1 a1 and xn an, then a1 times a1 is a1 squared plus all the way up to an squared. So that result is actually positive, a positive integer. So at least I know this set is not empty. Of course, we have to assume that at least one of the candidates is non-zero, because if they were all zero, then it's meaningless. So, and again, according to the well-ordered principle of natural numbers, if we're given a set of positive integers, right, natural numbers, there exists a minimum element. So therefore, I know that there exists a minimum, so let's call that S0. So I have two jobs. First, I want to claim, that's my claim number one. I want to claim that S0 is my biggest common divisor. In other words, I want to show that dj is actually no larger than S0, right? So in order for S0 to qualify the greatest common divisor, it has to satisfy two conditions. First, it has to be larger than or equal to than any common divisors of those candidates. Second of all, S0 has to divide every single one of them, right? So claim number two. S0 has to divide AJ, where J is equal 1 all the way up to N. And here, J is equal to 1 all the way up to R. Let's just assume that there are a number of different common divisors of these candidates. First of all, let's just prove claim number one, see if it's true. So to prove this is true, let's find out if DJ, as long as I can show DJ can divide this combination, right? So let's just assume S0 is already some linear combination. Let's just say x1 a1 plus all the way up to xn, an. Then I want to show dj actually divides S0. Right? Because first of all, dj is a common divisor of a1 all the way up to an. Therefore, dj divides a1, dj divides a2, dj all the way up to divides an. So obviously, dj divides the linear combination. Right? So dj divides S0. So since dj divides S0, it's easy to see that dj actually is no larger than S0. That is obvious. So claim number 1, proven. So claim number 2, I want to show S0 divides aj, right? So if otherwise, proof by contradiction. If S0 does not divide aj, what will happen? So in that case, aj can be written as cube j, some quotient times S0, my divisor, plus a remainder, rj, where rj is strictly larger than 0 and strictly less than S0. Since I assume S0 does not divide aj, therefore our remainder has to be not equal to 0 and has to be strictly less than S0. In that case, let me just rewrite rj into aj minus qj times S0. All right, so since I know S0 is already a linear combination of the candidates, therefore if I times qj is also a linear combination, and I have aj, so all in all, this is still a linear combination of my candidates, right? So therefore, rj can be written as a linear combination. And of course, rj is at the same time strictly less than S0. So in other words, I've found another linear combination of my candidates which is even smaller than my minimum element, right? Which is a contradiction. Right? This is already a contradiction. Right? First, I've proven that S0 exists. S0 is the minimum element, right? The minimum possible combination of the candidates, right? Out of all the possible positive integers, this is my minimum integer in terms of a linear combination that yields this positive integer. Somehow I've found an even smaller integer, smaller than S0. That's a contradiction, right? So claim number 2. So in other words, S0 actually divides aj. So this is proven. So really, the S0 is really my greatest common divisor, right? Equal to D. D is my greatest common divisor. So this, of course, in the special case where n is equal to 2, then we have x1 a1 times x2 a2 is equal to D, greatest common divisor of a1 and a2. So that is essentially Basel theorem. Of course, the same result can also be proven by using Euclidean algorithm. And in particular, if A1 and A2 are coprime, then we have a linear combination where that equals to 1.